Okay, so let's continue with the constant coefficient ODE. Yesterday, I mentioned that this one called the Euler's identity. This is not precise enough. Actually, this should be called Euler's formula. But of course, it's just a name. Euler's identity actually refer to the one like exponential to I pi plus 1 equals 0. This is the special case of the Euler's formula. Euler's formula is this one. So when you plug in omega t to be pi, then you will get this, because cosine of pi is -1, sine of pi is 0. So you will have an exponential to j pi or I pi plus 1 equals 0. Okay, so we can briefly review what we actually need to do. So when we try to solve the constant coefficient ODE, we try to make the right-hand side to be 0, and then we solve for the homogeneous solution or the complementary solution. Then we try to solve for the particular solution. It depends on the what g of t is, what is the form. Some of the form you can just use some assumption to assume, this is the form for the solution for this type of g of t. Then, yeah. And then finally, after we getting the homogeneous solution and the particular solution, we can just add them together to form the complete solution, and then we can use initial value if we have to determine the unknown coefficient in the homogeneous solution. So when we try to solve for the homogeneous solution, we try to plug in the original function to be an exponential function. And it works because when you try to take the derivative of this function, you multiply it by s. Similar to what you have done in the Fourier transform. When you take the derivative, you multiply it by j omega, something like that. Okay, so after making this substitution into the original homogeneous equation, and then you will get this algebraic equation, and then you can try to solve it. And yeah, so most useful case is actually this one. The most complicated one, b squared minus 4ac is smaller than 0. Then you will get the form like this. This is the real part of the root, and the imaginary part of the root is beta. Then the form will be exponential to alpha t times this one, cosine beta t, and the linear combination of cosine beta t and sine of beta t. Yeah, C1, C2 are arbitrary constant or unknown coefficient, need to be determined later. Okay, so let's take a look at some example. So the first one is 2x double prime. Double prime is the second derivative, minus 5x minus 5x prime minus 3x equals 0. So you can change this second derivative to s squared, first derivative to s, the original function to 1, and then you have a 2s squared minus 5s minus 3 equals 0. So solving this one is easy. You can just try to write it like 2, 1, 3, 1, and then minus. So you have a positive 3 and then negative 1/2. So you have something like this, C1 exponential to minus t minus half of t minus half of t, which refer to S1, and then C2 times exponential to 3t refer to S2. So this is the homogeneous solution, or actually the solution to this one, because we don't have anything on the right side related to the independent variable t here. So for the second one, if we have a x double prime minus 10x prime plus 25x equals 0, We can change this one to s squared, change this one to s, change this one to 1. So we have s squared minus 10s plus 25. Okay, so you can quickly see that this is a perfect square, which is actually s minus 5 quantity square equals 0. So s equals to plus 5, which is the repeated roots. So in this case, we will say x of t to be c1 plus c2t, because for repeated root, we need to multiply by t, and then exponential to 5t. This is the root 5t, like this. So for the third case, x double prime plus 4x prime plus 7x equals 0. So we have a s squared plus 4s plus 7 equals 0, like this. So you can still complete the square to be like s squared plus 4s plus 4 equals negative 3. So we have s plus 2 quantity square equals negative 3, and then take the square root on both sides. So we have s plus 2 equals plus or minus square root of 3j or I. So finally, you will get negative 2 plus or minus square root of 3i. Yeah. So in this case, the real part is negative 2. The imaginary part is a square root of 3. So we have an exponential to minus 2t. This part refers to the real part. And then we have a combination of a cosine of square root of 3t and sine of square root of 3t, the linear combination of these two terms. So this square root of 3 refers to the imaginary part. Yeah, so this is the 3 cases for solving a second order constant coefficient ODE. Yeah. Okay, so next part is to talk about how to solve some specific type of particular solution. Actually, it does not include arbitrary function for g of t, but this 1, 2, 3, 4, 5, 6 is more than enough for what we will use in bachelor course. Yeah, I think most useful case is something like polynomial, or a even more specific type is something like a constant on the right side, just like a DC source, something like that. Exponential function, not necessarily useful, but yeah, still useful. But yeah, actually the sinusoidal function, cosine or cosine, sine or cosine, not for tangent, because tangent takes the value to infinity, something like tangent pi over 2 is diverging, positive infinity, or for this one, pi over 2 minus would be something like that. It tends to infinity, so practically it will not exist very often. Yeah, so sine or cosine will be quite useful, because actually in signal system you're learning a Fourier series, Fourier transform. So yeah, for arbitrary signal, you can always decompose it into the sum of a different sinusoidal with a different amplitude or different frequency, different phase, and then you add them together to form arbitrary a signal. If it is periodic, you can use a Fourier series. If it is non-periodic, you can use the Fourier transform. Yeah. Okay, so this is a composite case of them. Maybe exponential times sinusoidal is more useful, but yeah, we seldomly use that. Usually, the most useful case is actually sinusoidal function. But for completeness, I just include them all here. Yeah, so other than that function, and then this may not exist, you may need to use a Fourier transform or Laplace transform to solve them. Yeah. Okay, so for the first type, which is I think the easiest one, if g of t is a nth order polynomial n 阶的多项式and we denote it as a p sub n means the order p of t. Okay, so now we can assume xp of t to be also a nth order polynomial. So this is an example. So we have this one, x double prime minus 2x prime minus 3x. So the right side g of t is a polynomial with first order. Okay, so the first step is of course to solve for the homogeneous solution. So we let the right hand side to be 0. So this is step 1. So we solve for it. We have s squared minus 2s minus 3 equals 0. And then we can see the two roots are -1 and +3. So we have the homogeneous solution like this form. This is a distinct real roots. Yeah. So we have two exponential function here. And so let xp of t to be another polynomial with the same order. This is first order. So we also let x of p of t to be a first order polynomial, a plus b t. Okay, and we plug it into here so that we have a plus bt double prime minus 2, this one, and then minus 3 times the original function equals 4t minus 5. Okay, so first order polynomial, take the second derivative will be 0. And then this one, constant, take the derivative will be 0. This one, take the derivative will be b. So we don't have the t here, so we have minus 2b for this one. And then minus 3a minus 3bt here. And then 4t minus 5. Like this. Okay, so next we try to rearrange the terms. So we have something like the first order term minus 3bt, and then on the right side we also have a 4t. And then these two terms are constant, only related to the a and b, but not the t. So we group them together. We have a minus 3a minus 2b here, and then 4t minus 5 on the right side. So they are equal to each other, which means that minus 3b should be equals to 4, and then this term should be equal to -5. Okay, so we can solve for this joint equation with two unknowns. So you can solve it, and then we get a and b. So finally, the particular solution is 23/9 plus should be minus 4/3t, like this. This is a particular solution. This is the homogeneous solution. And here we don't have the initial value, so that we just keep the C1, C2 here. And if we have the initial value like x of 0 equals something, x prime of 0 equals something, then we may be able to solve it. Later on, we will have an example with the initial value. Okay, so this is actually the first type, which is about the nth order polynomial. So next, we talk about the exponential function, or the polynomial times the exponential function. So if g of t is an exponential function, exponential to alpha t, we can also assume the particular solution to be also an exponential function with the same exponent. Here we have alpha t, here we also have alpha t, but we multiply it by a constant in the front, and then we need to determine. And then if g of t is a polynomial times exponential function, like nth order polynomial times an exponential function, then we can also assume x of p to be like an nth order polynomial, and then multiply by this exponent. So this is an example. We still have the same form on the left-hand side, and then we have this one, polynomial times exponential function. So similarly, we have the complementary solution like this, and then for this one, we can assume something like, oh, this is the first order polynomial. So that actually we can assume it to be like a plus bt times exponential to alpha t. So we can just distribute it a times exponential to alpha t. The alpha is 2 here, so we have a times exponential 2t plus bt times exponential to 2t. Bt times exponential to 2t. Okay, so then we plug this one into equation 2. So we have this term double prime minus 2 times this term prime minus 3 times this term equals 6t minus exponential to 2t. Okay, so this is a bit more complicated, but still not so difficult. So take the second derivative. We have 4 here, and then take the second derivative here. We need to use the product rule because this is a function of t, this is another function of t. So we have a double prime of this one, which is 0, and then prime of this, and then first derivative of this times the first derivative of this will be this term. I think, yeah, happy with this term because you still need to multiply by 2 here. So you have 4b exponential to 2t for the middle term, and then take the second derivative of this one will be 4bt exponential to 2t. Actually, you can double check it by yourself if you don't believe, and then you can just follow all the things so that finally we can collect the terms together. We have t times exponential to 2t. Like this one include this one, and also this one. So we have 4b here, and then negative 2 times 2b will be minus 4b. Minus 3 times b will be minus 3b. And then next, we have an exponential to 2t. So we have this one, this one, this one, this one, okay, and also this one. So we have this one 4a plus 4b, and then minus 4a, and then minus 2 times b minus 2b minus 3a. Altogether 5 terms for this one equals 6t times this one here, and then 0 times this one because we don't get this term. We don't get the 0 order polynomial on the right side. So we have a 0 here. So actually the red parenthesis equals to 6, and then the green parenthesis equals to 0. So we have this joint equation, and then we can solve for a and b. So finally, the particular solution is negative 4/3 minus 2t times exponential to 2t. So we have this one to be the particular solution. This is the homogeneous solution. So this is a bit more complicated. And the next case, it will be more useful. The first one is about the sinusoidal function, and then the exponential times the sinusoidal function. And then the most craziest one is polynomial times the exponential times the sinusoidal. Okay, so here, yeah. So if it is a sinusoidal function, either sine of beta t or cosine of beta t, or include both of them, then you will assume the particular solution to be also sinusoidal function, but a combination of a cosine of beta t and sine of beta t. Even you only have a sine of beta t for the equation, then you still need to assume the particular solution include both. if the original differential equation already include both of them, then you still only assume these two terms. Yeah. And if it is exponential function times sinusoidal function, like this, exponential to alpha t times sine of beta t, or this one, then you assume exponential xp, the particular solution, to be exponential to alpha t times this one, which means you multiply this one to this term here. Yeah, and the final case is if it is polynomial times exponential times sinusoidal, then you also assume the particular solution to be polynomial times exponential times sinusoidal, like this. Yeah. Okay, so let's take a look at this example. We have a x double prime minus x prime plus x equals 2 sine of 3t. So the first step is to find the homogeneous solution. We let the right side to be 0. So we have x double prime minus x prime plus x equals 0, like this. Okay, so this one is actually s squared minus s plus 1 equals 0. So you will have s squared minus s plus 1/4 equals negative 3/4. So you just divide, actually separate 1 into 1/4 plus 3/4, and then move this one to the right side. So this one is a complete square, so it becomes s plus 2 quantity s minus 2. S minus 2. Oh, sorry. S minus 1/2 quantity square equals negative square root of 3/2j, something like that. So s should be s will be 1/2 plus or minus here, plus or minus square root of 3/2j, like this. So we have the real part here and then the imaginary part here. Okay, so this is the homogeneous solution. And then this is sinusoidal function. So we assume the particular solution to be also a sinusoidal function, but including both cosine and sine. So we plug in this one into the equation 3. So we will get this one double prime minus this one prime plus this one equals the right side. So we will get this one, we collect all the terms together, cosine 3 of t, sine of 3 of t. So on the right side, we only have sine of t, so we have a 0 times cosine 3 of t plus 2 times sine of 3t. So the red parenthesis equals 0, and then the green parenthesis equals plus 2. So you can solve for this joint equation, you get a and b. So finally, the complete solution will be the complementary solution plus the particular solution, like this. Yeah. Okay. So actually, when you try to solve for the constant coefficient ODE, you need to memorize some of these steps. You may feel like, oh, you are doing mathematics. You need to remember many of these terms, many of these procedures. Actually, it is based on you don't assuming that you don't have too much mathematical knowledge. Then you need to remember these steps, and then you follow these steps, and then you get the correct answer. And of course, you feel like why the original person can come up with this procedure. Yeah, actually, if you need to know why, then you will stick for the Laplace transform. Then you will see why it will be like that. It will tell you why you need to make this assumption, because the Laplace transform of the differential equation will come up with this term, and then finally, after you're solving the the Laplace transformed differential equation. You will get the Laplace transform of the solution like that, and then you take the inverse Laplace transform, then you will see the form of the solution will look like that. Okay, actually there is a glitch for this method, so we need to do some modification to it. So for some of the case, if you still only follow the original rules, then there may be problem. So let's see an example why it will be a problem. So here is an example: x double prime minus 5x prime plus 4x equals this one. So you still follow the procedure. So you solve for the homogeneous solution, x double prime minus 5x prime plus 4x, let the right hand side to be 0. So you will get s squared minus 5s plus 4 equals 0, s equals 1 and 4. So you have an exponential to t and the exponential to 4t. So you can quickly see that this is exponential to t. This is also exponential to t. If you still assume the particular solution to be this one, then there will be no solution. You can, if you don't believe, you can try, because this one already tells you that if you just plug in this one to the original differential equation, you will get 0 on the left side. It can never be equal to 8 times exponential to t, because original method already tells you that. So if you just make this assumption, it's clear that we cannot find 8 for 4, as exponential to t is a solution to this homogeneous equation. So alternatively, we should assume xp of t to be this one and substitute it into 4. We can find a to be yeah. You may still why we need to multiply by t. Last time I already tell you that. Let me try to show you. So let's see. We have an x double. We have x double prime minus 4x prime minus 5x prime minus 5x prime plus 4x equals 8 exponential to t. So far we know that the complementary solution is a times exponential to t plus b times exponential to 4t. Okay, so xp of t originally should be a exponential to t, but it won't work. It won't work. Just mention, maybe I just put a c here because we already use a and b. So put c here. So actually we need to multiply by t, but you may ask why. So we try to make it like g of t to g of t. This g of t is not this one. So yeah, maybe I can use g of t, but you try to distinguish t, g of t, and then take the first derivative minus 4d exponential to t g of t equals 8 exponential to t. Okay, so take the second derivative will be like second derivative of this one, c times exponential to t, because exponential to t take the derivative will be itself. So take the second derivative will still be itself. So like this. And then we have 2 times c, and then the exponential to t, g double prime of the t. And then minus 5, minus 5, and then we have c, and then the first derivative, exponential to t times g of t. and then plus first derivative of this. So we have a c exponential to t times g prime of t, and then plus 4 c exponential to t g of t equals 8 exponential to t, like this. Okay, so we can collect the similar terms. So we have a g double prime c exponential to t g double prime of a t. And then we have a first derivative. So we have this one and minus 5 this one. So this is 2c, this is minus 5c. So we have a minus 3c exponential to t g prime of a t. And then next we have this one. Is the original function. This one is the original function. So you can see this is plus 1c. This is minus 5c. This is plus 4c. So all of them cancel each other. So we finally equals 8 exponential to t. So you can see here, we don't have g of t. So we can see exponential to t is not 0. So we can cancel it. Like this. Okay, which means yeah. So we have a c. G prime. Yeah. So we have a c times g double prime of t minus 3c g prime of the t equals 8. 5 4 4 C double prime of t. Let's see. G double prime of, or maybe I just, let's see. G, okay. 5 minus 5 no. 4. No, this one. Exponential to t. Let me see. This one double prime times this one, 2 times this prime, this one. And so the g double prime of t. Minus 5 exponential to t g of t plus exponential to t g prime of t plus 4 exponential t of t. So we have this one cancel. Yeah, so we have this one cancel with this one and this one. Okay, so we have so like this. So we have a g double prime 2 minus 3, 2 minus 5 is mm, mm, mm. Should we? Oh, I see. Oh, I see. So yeah, yeah, I see. So we can just take the integration on both sides. We can just ignore C here. We can just ignore C here. Yeah, just keep all the C. So we can just take the integration on both sides. So we have a G prime of T minus 3. G of T equals 8 T plus a constant, maybe a constant C here. So you can see, yeah, there will be something like this one here. Yeah, so this one occurred here. Maybe I get some stuck here, but actually, if you calculate correctly, then you will get G of T to be a linear function, and then you will finally find that, yeah, actually you need to multiply it by T here, and then you plug in this one back to the original equation, then you will find A to be negative A over 3. So this is actually the grid here, and yeah, this is how we need to solve it. If the particular solution matches some of the homogeneous solution, matches a term in the homogeneous solution, then we need to multiply by T. If this one already repeated, just say if this is if for some case xd of T to be C1 plus C2T exponential to T, then you will need to assume xp of T to be something like a T squared exponential to T, something like that. So if you repeat with this one, then you multiply it by T. If it still repeat, then you multiply another T again. Yeah. Okay. So let's take a look at this initial value problem, which means that we not only have the ODE, but also the initial value. So yeah, we can finally determine the unknown coefficient. So this one, we try to solve for the homogeneous solution first by making the right side to be 0. So we have x double prime plus x equals 0. So we have s squared plus 1 equals 0, s to be plus or minus j. So we have cosine of t and sine of this is sine t. So we assume the particular solution to be cosine of t plus sine of t. But this will excite this homogeneous solution. So we need to multiply it by t here. Okay, so actually we can just plug in this one into the equation 5. So we have equals on the right side 0 plus 4t plus 0 cosine of t plus 10 of sine t. Then we can compare the coefficient. We have a equals 0, b equals 4, negative 2d equals 0, negative 2c equals 10. So we have a 0, 4 minus 5d, 0. Illusion. With this C1, C2 to be the unknown coefficient. So next step is to determine the C1, C2. using the initial value. So this is the complete solution. And then we know x of 0 equals 5. So we can just plug in 0 here. We will get x of 0 to be c1 times cosine 0 plus c2 times sine of 0 plus 4 times 0 minus 5 times 0 cosine 0. So on the left side, we only have c1 because cosine 0 is 1 equals 5. So c1 is 5. And then this one, we can take the first derivative, x prime of t. So we get this expression. And then we can plug in 0 here because we know x prime of 0 is 1. So we can plug in 0 here. So we get this expression to be 1. Then we can solve for c2 to be 2. So finally, the solution of equation 5 with this initial value is 5 cosine t plus 2 sine of t plus 4t minus 5t cosine t. So with the initial value, we can solve for the complete solution. Okay, so this is pretty much the summary for solving constant coefficient ODE, and let's take a 10 minutes break and then we will enter chapter 32.